Okay, so hi everyone. Today I'm going to talk about fast algorithms for computing the Cactus representation of minimum cuts. And this is a joint work with Tachpong Saranurak and Shang Huang. I think Shang is now an assistant professor in National Taiwan University. And all right, so let's start with the problem. We consider the min cuts problem, and now we instead of in the last lecture, we want to compute just the one min cut or the value of the min cut. Now we want to list all the min cuts. So we are given weighted and divided graph G, and we want to find out its min cut. So recall that the min cut is defined as a partition of the vertex set, such that the sum of all the edges weights across the cut is minimum. So for example, in this graph, let's consider it's a simple graph such that all the edge weights are units. Then it's this is its min cut, which has a weight 3. And we know that there are at most a quadratic number of min cuts on the graph, which can be shown like as an algorithmic proof by Karger, which is might have been taught in a course. And naively, if we list all the min cuts, it requires cubic time or space. So for each min cut, we can just list the vertex set, like the A, and it takes linear space to store it. So in total, naively, it will be cubic. And the question now is, can we do better? Both in time and space. And it turns out yes. So in this talk, we'll see an algorithm with near linear time to compute the compact representation called Cactus representation, which just takes linear space, and it inherently captures all the min cuts. So any question about the setting? Okay. So good. And now, before introducing Cactus representation, let's see what is a Cactus graph. So maybe let me, let's do it. So a Cactus is a graph where every edge belongs to at most one cycle. So you can see these are Cactus graph, right? So note that a vertex can appear in multiple cycles, but an edge should just belong to one cycle. At most one cycle. So we know that tree is a fundamental and a simple concept in computer science, which appears in all the data structures and algorithms. And what about Cactus? So this figure comes from Professor Bob Tarjan's homepage, which is his favorite topic on self-adjusting binary search tree. And what about Cactus? It seems like Cactus is cute and seems not that powerful as tree, but in this talk you will see some fun facts about it. So so our algorithms on Cactus, we know that it's So let me first introduce something about Cactus in the theory world, right? So we know that there are some graph algorithms which are NP hard for general graphs can be solved in polynomial time for Cactus, right? So such as some facility location problems or other combinatorial optimization. Yeah. So and it is even implementable. So we can see these problems in ICPC and OI, such that but they are hard to implement. It's if you search on code sources and you see the problems and you sort it by the hardness, like 3500 are the hardest one, and the Cactus are the hardest. Yeah, I don't know if Basheng have seen any Cactus problem at your age. Yeah, but they are interesting problems, and we also see Cactus in topological graph theory, such as this result, which defines a maximum genus. The maximum genus is defined as like the maximum so given a graph, like consider the maximum genius such that the graph can have a cellular embedding on it. Cellular embedding means you can embed a graph such as every face is homomorphic to an open disk. So I'm not a topological guy, but intuitively it's like there's a relation between graphs and embedding on these topological.
So what does genus 0 mean?
Say genus 0 you can embed it on a planar graph, and genus 1 is you embed it on a torus. Okay. And so here they define this maximum genius is that in regards to the cellular embedding is that every face you want it to be homomorphic to an open disk, and it turns out if you embed a cactus on a torus, you cannot make it. So you can only embed it on a sphere, on a planet.
Okay.
On a planet, yeah. Yeah. So I mean these are some fun facts. I would say they are interesting, but not that surprising. Because like you have this cactus is the structure is simple, so it makes sense that you have a fast algorithm, and there are cycles. It makes sense that it have some analog in the topological world. But I think today we'll see a fun fact for cactus in combinatorics, which I think this really surprised me when I saw it. When I saw it for the first time. So it is said that cactus can be used as an edge sparsifier of linear size that exactly captures all the global mincuts of some graph. So given some graph G, there's always exists a cactus graph H, and the mapping phi from the vertex set of G to the vertex set of H, such that any mincut in G corresponding to a mincut in H. And vice versa.
Sorry. So here it's also allowed that you have a node that is empty.
Yeah. So I will introduce formally this notion in the next few slides. Yeah. And this really surprised me a lot because so it seems to be the oldest edge sparsifier, and it's hard in the beginning to relate a cactus graph to all the mincuts, right? So, but you will see in this talk we will give not only an algorithm computing the cactus representation, but also an algorithmic proof that's why the structure is a cactus. Yeah. So, any question?
On the high level, how is this like different from the Gomer-Hu tree, just on preserving all mincuts?
Yeah, good question. So, for Gomer-Hu tree, it preserves all pair mincut,
Yeah.
and but it doesn't capture all the mincut. Say a very good example is a cycle versus a complete graph. So in both cases, all pair mincuts are the same. So on a cycle, any pair they all have a mincut of size 2, and say a complete graph. Say if you can say you have a weighted graph, so you can normalize it so that you can make all pair mincuts are the same, right? But they have different structure on the global mincuts, like all the global mincuts. A cycle it have quadratic number of global mincuts, but on a complete graph, you only have a linear, the exactly global mincuts, which are the isolated vertex. Yeah, and you will see, you will appreciate cactus representation more when I formally define it. So given a graph, this graph, and I use a bold line to represent an edge with weight 2, and a thin line to represent an edge with unit weight. And in this graph, you can see the mincut is size 4. Right, and now I will tell you that this graph H with the mapping phi that I write down on those, it together is a Cactus representation that captures all the mincut of G. For example, this is a mincut. Say you cut two bold lines, right? And it corresponding to a cut in the cactus, which is a mincut of the cactus. And this is also a mincut. That is the vertex partition are the same in G and H. And this is also a mincut.
So it's allowed that in this H you can also have edge weights.
Yeah, and good question. So in H, all the tree edges means the edge doesn't belong to any cycle. All the tree edges will have weight 2, and all the cycle edges will have weight 1. So
this 2 and 1, like it's for this example. In general, what does this mean?
Oh, actually, it is true in general. I mean, or you can say this is lambda and this is lambda over 2.
Oh.
Yeah, and so that you can see that the mincut will always be you cut one tree edge or you cut two edges which belongs to the same cycle.
Okay, so even the original graph doesn't only have like weight 2 and 1 edges.
Yeah, original graph can have arbitrary weights.
Okay.
But the cactus graph we will show that there always exists such a cactus, such that it's the weight are just lambda and lambda over 2.
Okay.
It's just two kinds of weight. So it really surprised me when I saw this. Yeah, and also you can see that the phi can be neither injection or surjective, right? Neither injective or surjective. Okay, any question about this definition? Okay, yeah, this theorem proved by Derandomize et al. In 1976, and it's quite short. It's 6 pages, 5 pages proof. And today we'll give algorithmic proof of that theorem plus these results. For randomized algorithm, there was an algorithm by Karger and Karger in 2009, and we speed up their algorithm. And for deterministic algorithm, before our results is quadratic. And this is the first near linear time deterministic algorithm. So and we also use their result by I think there's Li Zhao Wang, which was the paper presented last week, right? So, but even with their result plus this one, they didn't make it deterministic. So there are more inherent randomized step in Karger and Panigarhi's paper, so that we also de-randomize their algorithm, so that we can make it fully deterministic. Yeah, and okay, so yeah, so this is the first part. This will be the first part of our lecture. Like it's this result, and if time permits, we will also see the result for computing the Steiner and Steiner cactus. Yeah. Yes. So this will be maybe the first half an hour, and the second half will be Steiner. Yeah. Okay. So let's first see. Okay. So we will first see the tree packing theorem. Review the tree packing theorem that we talked about last week, and then we'll define minimal min cuts and show how to compute the cactus based on that, and then we will review, or I think Hua Xiong just high level describe the idea, but we will formally talk about Karger's two respecting min cut algorithm, and in the end, I think I will just high level describe how we leverage it to compute the minimal min cuts. So okay, recall that tree packing is a set of weighted spanning trees such that the total weight containing edge E is no greater than the weight of E in the original graph. For example, this green tree, right, it's a spanning tree. And this pink tree is also a spanning tree. And if you pack both of them in the graph, you can obtain a tree packing of value 2. Right? So you can see that for the line with 2, you can pack both tree on it. And for the thin line, you can just have one tree. Right? So this is a valid tree packing. And it turns out this is not a coincidence. In 1961, Nash-Williams proved the following theorem that Pasha mentioned last time. Any linear graph with a mincut C contains a tree packing of value at least C over 2. So I think the proof is just by duality that you find the duality is the partition, the max of the edges cross of some partition over the set of partitions. Okay. And it turns out this is useful for combinatorial algorithm. So let's first define what is a k-respect cut. So a cut is said to k-respect the spanning tree if the spanning tree contains at most k edges of the cut. For example, this cut is 1 respects the green tree and 2 respects the pink tree. Right? It crosses 2 edges on the pink tree. And now, based on Nash-Williams tree packing theorem, we have in a tree packing of value at least C over 2. For any mincut, half the trees by weight cross the mincut at most twice. So it's just by counting. Right? You cannot have more than half cross at least 3. Then you just sum them up. It's a contradiction. For example, this cut. 1 respects the pink tree and 3 respects the, I think it's 1 respect to the pink tree and 3 respect to the green tree, so there's a title. And this cut is 2 respect to both the green tree and the pink tree. So, so here's the theorem. Based on the lemma, in near linear time, we can construct a set of log n spanning trees such that each mincut respects at least a third of them with high probability. So I think Kwashian also mentioned this theorem last time. So the idea is, if your graph is dense, it seems that you cannot directly apply the lemma, right? You want to first sample the graph, and then you compute the tree packing. So what is required when you sample the graph is that it preserves the cut approximately, such that every min cut will be preserved within an epsilon fraction, and any cut will be preserved. It's not preserved. It's not reduced to smaller than anything. Actually, we don't need that. Yeah, it's just one side is enough. Yeah, I think you just need to sample the graph G such that any min cut in G will be 1 plus epsilon min cutting H. And meanwhile, H is sparse. And that's enough to apply the lemma and to conclude the theorem. Yeah. So this was used to compute the min cut in near linear time by Karger. And we know from the last lecture, this singularly Raoult one, their results gives the first near linear time result for the deterministic algorithm. So now the difference is that now it is not with high probability, but it's for sure that it's to respect 1/3 of them. But it is slightly worse in the parameter that is polygon. But I think before their result it's more than polygon. So that's how they give the first near linear time algorithm. Okay, so any question about tree packing? So the reason we want to reduce the problem to the cut that true respecting the spanning tree is that it greatly reduces the number of possible cuts that we are considering, right? So with this true respecting trick, we are just considering near quadratic number of cuts. So even you just enumerate it and compute it is not so good. It's not too bad, and we'll see how to use data structure to speed this up to compute the minimum cut. So any question?
Maybe one quick question.
Yeah.
Here, I guess in this in this talk, are the weights allowed to be real numbers, so they have to be integer? They can be integers. They have to be.
Yeah, good question. So in all these mincut algorithm followed by Kargers, they are all arbitrary weights. Can be real or
Okay.
yeah, they are arbitrary.
Okay.
Yeah, I think you might wonder why here it's kind of an integer, right? I think one of the reason is that you can just slightly perturb the weights so that to make it integer at the very beginning, and then sample to the sparsification, and then do the tree tagging.
I actually mean the weight of the trees in the tree bag. Are these weights allowed to be real numbers?
Yeah, so in the lemma, yes, it allows to be.
Yeah.
But here in the theorem, in both Kargers and this particularly Rawan's theorem, they are just spanning trees. You can say with unit weight.
Okay.
They are just it's really a set of this number
Yeah.
of spanning trees instead of the total weights add up. Yeah, the reason is that we do the pre-processing step of the sampling and so on to produce. Yeah, good question. Yeah, all right. So now let's see how to construct a cactus based on this. So I think it's not based on tree packing. It's we will define a minimum min cuts and see how to use them to compute cactus. So it's different from the first section, and later on we will combine both of them. So from now on we will fix vertex to be the root, and let's say in this talk let's fix the vertex A to be R. And now we define the size of a cut to be the number of vertices in the part that's not belonging to that's separated from R. Say a cut x v minus x, where R is not in X, is defined to be the number of vertices in X. So this is a cut of size 3. And the minimum min cut of a vertex is then the min cuts of the least size separating this vertex from R. For example, this is the minimum min cut of vertex C. And we also define this for the minimum min cut for an edge. Like it's defined to be the min cut of the least size separating the edge from the R.
So this edge cannot be part of the cut.
It cannot, yeah. It's like separating both of endpoints from R. Right, so you may ask, why it is unique, right? So why it can be like there are multiple min cuts of the same size? So it's by the structural reason. So we will define like two cuts to be crossing if each of x intersects y, x minus y, y minus x, and the complement of x using y. These four parts are all non-empty. So in this case, you can see they are crossing. And the lemma says if two cuts are crossing min cuts, then each of these four parts is also min. So in this example, the purple and the red cuts are min cut. Then you can see the left part, right part, and the singleton I, singleton J, they are all min cut. So any question about this lemma? So this is a very fundamental lemma, which we will use it throughout the whole talk. So it's simple and fundamental. So the reason is that the cut function is submodular. So I think now I will use a board to prove this. So it's not only by some modular. So I think some modular might only prove that these two are mincut. So let's use Cx defined to be the summation of edges that cross x. Let's put in x v minus x w v. And then this is a cut function, and we know that. Is it recorded?
Yeah.
Yeah. And we know that right. So this is a submodularity of the cut function, right? And we know they are mincut. They are at least they equals to lambda, and we know they are at least lambda because mincut is lambda. And we know that by the definition, these things are not empty, so they are valid cut. So they should be at least lambda. And this is greater than or equal, so they should be exactly lambda. So this proves that this guy and this guy are mincuts. And to prove the other two, they are by a similar result, similar lemma, but as submodularity, which is called polymodularity. But the proof are just literally the same, but with the other inequality called polymodularity, where you have this.
Yeah, I thought can you just plug in like the complement of x or the complement of y into the argument?
But then the intersection and union are
I guess the complement of x intersecting y is just y minus x.
complement. Oh right, because they are symmetric family, right? So this complement of x is also. Yeah, I mean, it's.
Okay,
Right, I think.
I'm not sure. Or maybe it's not.
Why? If you.
Oh,
If you. You mean this, right?
yeah.
Yeah, I think it makes sense. Makes sense.
Oh, okay, yeah. The left one is y minus x. The right one is the complement of x.
Yeah, I think there are multiple ways to prove this. Yeah. Right, so you can see the structure is very nice, and now we have proved this now. So if a minimal min cut of a vertex or an edge exists, then it is unique. It may not exist because there is no cut min cut separating this vertex to the root. Right. But if it exists, then it should be unique because I think we haven't fully proved it. So the reason is that proof by contradiction. If there are multiple minimal min cuts, then you take their intersection. Right? So this by contradiction, it is a smaller one. So it should be unique. By intersection, I mean you know that x containing this vertex separating v from r, where v is in x, and y also separating v from r, and you take x, you intersect y, which is a smaller one. Yeah. And now we can define this notion. We say a cut has a vertex certificate or edge certificate if it is a minimal min cut for some vertex or edge. So for example, I think no example. I think this is it. This is a certificate. So this red cut have the edge certificate J. So there is no no mincut of smaller size that's separating JL from A. Okay, so I think I want to define one more notion and we will see a theorem. So this is called a chain certificate. If a sequence of disjoint non-empty vertex subset satisfy the following. So I think with this figure it might be helpful. So for each I, Ci it has either a vertex or edge certificate or a chain certificate. So I'll say the Ci is defined to be this purple set. So C0 is a singleton I, C1 is this polygon containing 5 vertices, and C2 is the singleton J. And the singleton have the certificate because it has a vertex certificate because it's of course a minimal mincut of itself, right? They are mincut. And the purple one also have an edge certificate as a KL. Say for edge KL, it's a minimal mincut separating the edge from vertex A. And so they satisfy the first property. And the second, we ask for each I, Ci union Ci plus 1 has an edge certificate. So for example, I union the polygon, it has a certificate Ik, and J union the polygon, it has a certificate JL. Yeah, so this is the most complicated definition throughout the talk. So I think yeah, take some time to adjust it, and later it will be simpler. Yeah, so we just abuse the notion that the cut will be simply denoted by the set X and not containing the root.
Okay, so we have so we fix the cut.
Yeah.
And a chain certificate is a partition of X into this sequence of disjoint sets C0 to C0.
Yeah.
So we want each one of them to.
Yeah, each one of them to. It's recursively, like each one is a smaller subset and not containing R. And we want each one already have a certificate. And
okay, each one has a certificate, meaning that it has, in particular, it has to be a mincut.
Yeah, so I think the next lemma is if it has a certificate, it is a mincut. Plus, like the definition of the vertex or edge certificate, they are just a mincut. Recall that they are just a minimal mincut of the edge or vertex. So, yeah, good question.
So for each one of them, eventually it needs to be a mincut.
Yeah.
And also, it will have a certificate of some form.
Yeah, so that's why like 1 plus 2 already tell you like this X will be a mincut because this crossing. Basically, 2 is asking like it's a chain like if you write it down, like so. Okay, so the beginning is so these are C0 to C4, and the second property tells you these are all mincuts. So the first property tells you these themselves are mincut, and the second tells you the adjacent ones are mincut. And if you use the lemma, the crossing lemma that we have just introduced, you can see you iteratively use like you can see like any consecutive subset are mincut. And the whole thing, of course, it is also mincut. Yeah. So this will be our next lemma, but I've already proved it. Yeah.
And here you are. For 2, you apply the union of the consecutive 2 to have an edge certificate.
Yeah.
Okay, I'm just trying to understand why
you need an edge certificate.
Not the vertex.
I think we define it in this way to simplify the proof.
Okay.
Because in this case, we can show that if so a chain certificate will be unique up to reverse.
Oh.
So otherwise, if you define it the second one to be arbitrary certificate, say it can be again a chain certificate, then it will not be unique because you can combine these two as one combine two consecutive sets so that it's again a chain certificate for X.
Okay.
But in this case, it forces you to do a maximum chain.
Yes. So can it be a vertex certificate? I'm trying to understand what's the
Right. Good question. So vertex certificate doesn't cross with any other certificate because if a vertex certificate crosses with others, you can see that this is a vertex certificate of some B. If it crosses with others, there will always be a smaller, like a smaller mincut, a mincut of smaller size separating B from R, which contradicts to that this mincut is minimal for B.
Okay.
Yeah, this is a very important property. Yeah, so actually that's how we build up the Cactus. Like we first compute all the vertex certificate, and which turns out to be a laminar set. And we first build this tree structure because it's a laminar set. You can build a tree based on it, and then we bottom up build up the chain certificate. Yeah. So I think I will introduce in the next few slides.
Okay. Sorry, one more question about this intersection. I guess what you said implies that it's also impossible to have another cut that intersects with this cut but does not contain B. That's also impossible. Like the intersection does not contain B.
Yeah. So that's why I say that vertex certificate doesn't cross with any mincut.
Okay. So why is this not possible?
Because this is X, this is Y. X minus Y is also mincut. So by
X minus Y.
Yeah, by the crossing, it's all these four
Okay.
sets are all mincut.
Yeah.
So yeah, good question. So very good question. So that's why we define parity two as that. Okay, so yeah, this is already asked by Hachung. So for any vertex set which has a chain certificate, it's either a mincut or the whole vertex set. And we proved it here.
Is the converse also true, like any mincut?
Yeah, good question. This lemma.
Oh, yeah.
So every mincut on G has either a vertex certificate, or edge certificate, or a chain certificate. Yeah. Yeah, so you can see why we define this certificate. It's just we want to capture all the mincuts. And we will prove both lemma. So for so this cut have a chain certificate, and it doesn't have any edge or vertex certificate. So we only need these three definitions. And that lemma we have already mentioned. It can be proved by crossing property of the mincut. And it turns out this converse lemma is also proved by this crossing lemma. Why is it? So let me. Yeah, I think this lemma is yeah, I think maybe we are not going to prove this lemma. because it's a little bit complicated.
What's the high level idea?
Yeah, so high level idea is that if we consider these mincuts from size small to large, and if this mincut doesn't cross any mincut we have already iterated, then it should have either a vertex certificate or an edge certificate, right? And if it crosses, then we can show that it has a chain certificate by induction. But it cross with some mincut, and this is a mincut now we are considering, and this is another mincut. And we know that these are smaller mincuts, and they have a certificate, chain certificate or edge certificate or vertex certificate. And we just, if they have chain certificate, we can just break it to the maximal chain so that it satisfies our definition, and you combine these together. It's again, or maybe, yeah, there are case analysis, but if it is if it is a chain certificate, there are multiple cases, but I think you get a sense why it's true, right? Yeah, so this is just proved by induction. Yeah, any questions so far? Okay, so so this will be our theorem for this section. So given a graph, a tree packing, and the set of two respecting cuts representing the minimal min cuts of each vertex and each edge, we can deterministically compute the Cactus representation in I times arcman function plus n times the size of the tree packing. So if plug in the near linear time tree packing algorithm, it will be near linear time in total. Yeah, so the reason here is why we can afford to store all the min cuts. The reason is that we are using this property of tree two respecting tree, right? We just need to identify which tree is in the tree packing, and these two edges that you are cutting on the tree. So it's just a constant size you store a cut. And basically, the algorithm is just how we prove that every min cut have a certificate. It's just like you source the size of these two respecting minimal min cuts from small to large, and when you iterate some min cuts, you want to see whether it cross any min cuts you have already seen, and if not, you can just build like a tree structure. Like you add one node and you just connect all the min cuts that it contains to this parent. Otherwise, it forms a chain, and you will see a chain will be a cycle in the Cactus in the end, because a chain in the end there will be some larger min cut containing all of them, and so I will draw a tree in reverse order. So this is the parent, and it will connect a cycle of everything. Yeah, so here there in C0 there can be subtrees. Yeah. So this is the structure. So you can see a chain certificate, it it means that any consecutive subsequence will be mincut. So it corresponds to a cycle in the calculus. So the remaining part is we really reduce the problem to containment query. So given two mincuts that representing by these cut labels, we want to see whether they cross or they contain the other. Right? So
Okay, okay, I'm not sure what is the algorithm again?
So the algorithm is with scanning this minimal mincut from size small to large.
Okay, but in total they are
Linear.
like n square.
No. Minimal mincuts, there are linear number of minimal mincuts. So it's not all the mincuts. It's all the minimal mincuts for some vertex or edge. So each vertex and each edge, they will only have one minimal mincut. So we scan through this linear number of mincuts from size small to large, and based on how they contain each other and they cross each other, we build up the calculus.
So what about the? Yeah, so what happens to the cut that only has chain certificate?
For the cut that only have chain certificate, yeah. So it comes from that when we see that this cut cross with some smaller cut, it starts a chain, right?
Yes.
So then we will replace. So we are maintaining this hierarchical structure, and on top it will be the union of them, and we put a token on it, say that this is a small chain, this is some chain, and later it can be like you extend the chain by if you're scanning the next mincut, and it again cross with it, and you can extend the chain.
Yeah, I mean, this algorithm only actively looks at the minimum mincuts.
Right. So in our proof we show that all these chain mincut with chain certificate, they are also considered during this algorithm. So it's because the chain is by the second property of the chain, each consecutive two subsets are like is a minimum mincut of some edge.
Okay.
So when we look at them and we are doing this crossing or containment query, we will discover the chain along this algorithm. So it's not we cannot afford to consider all the mincuts because they are quadratic. So this is how we save the time.
I see.
Because we only consider the minimal mincut of vertex and edge, and we build up chain along the way. Yeah, good question. So I think that's all about the Cactus construction part. So now the problem reduced to computing the two respecting cuts, respecting minimum mincuts for vertices and edges. Right? Yeah, I think when I look at the time, I think I only have time to finish the first paper. So yeah, and I think the second paper is by completely different approach. It's by Max Flow, and I already gave a talk in Rutgers. So if you are interested, you can look up my YouTube channel. Okay, so next let's briefly review Karger's near linear time algorithm, and we will see how to leverage it for our purpose. So this is a framework of Karger's algorithm that you first compute a tree packing of size log n, such that each mincut tree respects to some of them. And the second, for each tree, you compute a minimum tree respecting cut on this tree. and you take the minimum over all the trees in step 2. So, and in our algorithm, the framework is almost the same, except that we want to compute a minimum mincut for every vertex and edges on the tree in the second step. So for each vertex and each edge, we want to compute the minimal mincut that to respect to this tree. And we take the minimal mincut over all the tree for every vertex and edge. And we build the cactus based on second step. So our contribution in this paper is we make step 2 and step 3 deterministic, faster, and more modular. So, so the first step is not our contribution. It's Hesingeri, Rao, and Wang's paper, the soda-based paper. And you know, in Karger's algorithm, the second and the third step, they are deterministic. But it turns out in the previous work by Karger and Panigarpi, their algorithm in the second and third step are randomized, one-color randomized. They bypass the second step. They are not computing all the minimal mincut for the edges. So they use their algorithm are sometimes compute these edge certificate, but it might err. So they can give you a wrong edge certificate. And they show that, okay, with high probability, they compute the correct figures. So our contribution is that we really make it cleaner. We always compute the correct edge certificate, and we are even faster. So okay, so I think we will have time to cover Karger's respecting mincut algorithm. I think it will. Yeah, it's a nice algorithm, and yeah. So, and for the fourth part, I don't think we have time. We will just talk about high-level idea. Yeah. So Karger's algorithm, we have already seen the first one in the last lecture, and I also briefly mentioned the high-level idea. It's just a sampling. And the second one is using we'll see it using the habitat decomposition and dynamic tree data structure. So let's first consider how to compute a one respect algorithm. So this is easier. So given a spanning tree, we want to find the smallest cut of G that cuts one edge of the T. But we need to consider all the non-tree edges, right? We cannot afford to enumerate all the edges on the tree and then enumerate all the edges to see whether it crosses the cut. So how to do this? So we ask when is this non-tree edge UV being cut? So the non-tree edge is cut if the cut in G cuts an edge on the UV path. So the idea now is that if we iterate an edge through the T, keeping track of the non-tree edges that cross the cut at T, across the cut at E, then we ask is there an order of edge that results in non-tree edges transition on and off the current cut just a small number of times? It turns out the answer is yes. We can use habitat decomposition. We split T into root to leaf path, and we continue the path to the child one with the most descendants. Then any root to leaf path requires at most log n color changes. Because if you see from bottom up, then when you see a color change, the size of the subtree will be doubled. Will be increased by at least a factor of 2.
Yeah, I just want to be clear. The color just means like you follow the child with most descendant that
right.
Inherits the color.
Right. Yeah. So the order will be what you said is we iterate edge in habitat decomposition order. It's just we are now on on the root, then and go to the left hand side, we will follow the blue path near the end, and then recurse, and then do the other branch. And then any non-tree edges will transition on of the current cut just the login times. Any question about the one respecting algorithm? So I agree that there might be simpler ways to do this. For example, you can just compute this common ancestor and put some tag on it and do some DFS. But I think this will be useful when we see the two respecting algorithm. So this is just some preparation. So we iterate edge in heavy light decomposition order, and we just so the second step can be yeah, I think it's high level. Like you need to, I think you need to do the pre-processing that you for each non-tree edge you just put a tag on this path where the color change, and you do some DFS. It's just that way.
Okay. When you move from a node to one of the, let's say to the first child.
Yeah.
In this case, the edges that are affected are the edges such that there's one endpoint in like all other subtrees.
Yeah,
of
yeah.
The parent.
Right.
Okay. As long as you have a way like to enumerate all those edges.
Yeah.
Efficiently.
Right. So I mean, you can even do it offline. You can just do some pre-processing, and you can keep track of all these edges. And now we want to ask, what if the card cut two edges on the tree T? Then when does this non-tree edge UV cross the cut? So the this non-tree edge is cut if and only if the cut in G cuts exactly one edge on UV paths on T. So if they cut two edges, then the cut doesn't cross its non-tree edges. And zero, it never cross it. So only in this case, this edge will contribute to the cut. Only in this case. So how can we leverage our one respect strategy so that it works for two respecting cuts? Now we cannot spend like quadratic time checking all the cuts, right? So we want to make it more efficient. So it turns out this top tree data structure is perfect. So it supports the following operations, like path add. We want to add a weight to all the edges on some UV path, or non-path add. So it's just a complement. You can just maintain some global variable and subtract it, right? And we also want to query the minimum. And all these operations can be maintained in logging time. I think it's just a dynamic tree, but with this global query minimum.
I thought it's just a heavy light decomposition because the tree topology, the tree structure is fixed. There's no link cut.
No, I think we need top tree to support the third one.
Okay.
Global query, minimum query.
Okay.
Yeah. Right. So we'll see with this data structure, we can now query what's the other edge we will cut. So still we want to iterate an edge E on the tree, and then we will use the data structure to query the other edge. So so if E is on the so let's observe some more properties. If E is on the UV path, so any F of the UV path. So any F of the UV cut will cut UV. Is this clear? I mean, for the two respecting cut, if one edge is on the UV cut, the other should is not, then it cuts the UV. And conversely, it's V is off, then any F on the UV cut plus cut UV. So these orange edges contributes. So UV will contribute to these orange edges. So this might remind you of the top tree data structure. This is off path and this is on path. So this corresponds to the add path and add no path. So yeah, path add and no path add. Yeah. So we just use the top tree so when we switch from this green to that green, we just do a modification. We call this path add and non-path add, and that's it. And we just use a query minimum to find the minimum F that we want to cut. Is that clear? Yeah, that's all for the tree spectrum algorithm. Yeah, and yeah, so Karger's near-real time algorithm is pretty simple. It's just covered in the third section. And to compute the minimum mincut, yeah, this is very technical. I would say. So this is the most technical part in our paper. It's like more than 20 pages and take care of all the cases of these minimum mincut. But on a high level, it's still using this crossing property that you want to find, say, some mincut separate this vertex with the root, and some other cut, then you cross them, you can find some smaller one. And this lemma is very powerful, and it can be used so that we just overall time to compute all these linear number of mincuts turn out to be near linear. So I think we don't have time to cover this. And yeah, this is a summary of part one. I still have some time to briefly introduce the second one. Yeah, any question about part one? Yeah, we have seen an algorithmic proof of that theorem. And a high-level idea of our algorithm, like complete analysis of Karger's algorithm.
Okay, so for the randomized algorithm,
Yeah.
so it seems that the second and third step, they are not the bottleneck. Is that?
For randomized algorithm?
Yeah,
for randomized algorithm, it is. So I think the tree packing algorithm runs in I'm plus n to the log cube in Karger's original, like the 2000 paper.
Okay.
And the bottleneck is that for each tree in the tree packing, we need I'm times log squared time to compute the minimal mincut for every address. So even this will be a bottleneck for the global mincut algorithm, not the Cactus.
So what was the running time that you showed earlier that has this inverse arcman function?
Which one?
So you showed some running time that has
Yeah.
the inverse arcman.
Right, good question. So that one is like given all these labels of minimum mincuts for minimum mincut for every vertices and edges.
Oh.
And you want to compute the Cactus.
Oh.
So it's just a containment query. So it makes sense that you only have an argument because of decision union DSU.
Oh. Oh.
So we have seen that the fastest. I think we have not seen in our seminar, but the result is that for the if you want to compute the value of one global mincut, it's m log squared. So it's there is a log gap. So if you want to compute all the mincut, you just need to pay one more log factor, which is pretty good. All right, so yeah, let's start part 2 and for 2 minutes. So in this paper, we now consider the Steiner mincut. What is Steiner mincut? So it is covered. So we want to find a.
You can minimize by clicking the left.
Okay. So we want to find a subset. Oh no, we want to find a. Yeah, we want to find a subset of some of the terminal sets, such that the cost to disconnected x from t minus x is minimized. So let's see some example. So a t mincut is a partition of t. Yeah, it's just what I said, like a partition of t that minimum possible value cut among the all non-trivial partition of t. So for example, in this case, the global connectivity is 2, but the Steiner mincut is 2. If you want to separate these red vertices, at least you need to disconnect these 3 edges. Okay. And for this, the Steiner mincut is 2. And here is a theorem that says you have again the Cactus graph that preserves all these t mincuts for a given graph. So for this G and this set of terminal vertices, the corresponding Cactus is this. So is the definition clear? Right. So I want to emphasize that we are not preserving all the Steiner mincuts, but we are preserving all these possible partitions of the terminal sets. I mean, here, if these orange vertices are terminals, there can be many mincuts there, like even exponentially many, right? Obviously, there can be more than quadratic, and here we are just constructing a Cactus of size 2 with this single edge. So it actually preserves the information that how you could partition the terminal sets with a standard mincut. And here is the result for arbitrary graph. The state of the art is Derandomize and Wittstein in '94. They compute this Steiner Cactus via T max flow cost. And we speed it up by just using polylog max flow cost. And this is an analog in the hypergraph. So for hypergraph mincuts, it means that you can, so you still have weights, it's a weighted hypergraph, and you just remove a set of edges with the smallest total weight, such that it disconnected the graph. And by Flanner and Jordan, they show that there exists this linear size hypercactus graph that preserves all the mincuts of a given hypergraph. So, so you can see, so in the hypercactus, they show the following. So recall that in the cactus we have just 2 kinds of weight, right? On the tree edges we just assign a lambda, and on the edges, for the edges on a cycle we assign a weight of lambda over 2. And here is it's almost a cactus instead of there could be hyper edges with weight lambda. And it said that by removing these hyper edges of rank R, you partition this cactus to hypercactus to R parts. So it says that there exists such a hypercactus that preserves all the mincut in the hypergraph. Yeah, this is even more general. It's not only for hypergraph. Actually, they prove that this is for any symmetric crossing family. Actually, I need to check, but this is more general. Right. So, and we show the algorithm. So P is a summation of the rank of the edges. So P is just the input set. Yeah. So I used to plan to talk about this result, but but now I think only 5 minutes left. Let's keep it for question. Maybe let me show. Okay. Yeah, so today we only covered the first part. I think only, yeah.
So what is this element cut cactus?
Yeah, element cut is given a graph and a set of terminals. Now you can cut non-terminal vertices or edges. So there are weights on the non-terminal vertices, on the signer vertices.
Okay.
And the element cut is that you can the mean cut of cutting these edges and non-terminal vertices.
Okay. Cutting a vertex is like remove this entire.
Yeah, remove this entire vertex and say all the adjacent edges.
Okay, I see.
Yeah, and it turns out this Flanner and Jordan's theorem also applied to this element cut.
Okay.
And for general submodular function, I think the structural result is less known, and even compute the minimizer is still, so there is still a gap. I think last year lunch they mentioned, different art mentioned this open problem, and also for near mean cuts, it's there is analog called polygon representation, and it runs in quadratic time, but more than quadratic time, but I think it's so this representation could take quadratic size, like a square, and the algorithm is a little bit worse. It's to the 2 plus epsilon, where epsilon is a near mean cut that you want to maintain. But I think it's harder. I mean, the algorithm is already pretty good, I would say, and it's pretty close to quadratic.
Yeah, I'm curious, what is this polygon representation?
Yeah, so it's very similar to the Cactus, instead that you plot the vertices onto this plane, and the polygon is that here is a polygon, and this